from an x-intercept or something like this, I got two ways to go. I can leave it like this and put 0 in for y. And I can solve that, get the x minus 3 squared term isolated.
Plus.
X equals 3 minus 2, so that's 5, or 1, right? Or I can multiply this out. And find out where that thing equals 0, in which case I can use my Casio after I have it multiplied out correctly. Let's see. Where's the minus, oh, minus 15? So if I do it that way, minus 3 plus 18 minus 15. Five and more.
Wait, what I'm not really finding is how you get the one.
It's right there, it says x equals 1.
No, but the other way.
3 plus 2 is 5, 3 minus 2 is 1. You've got plus or minus in front of, I don't know. So either of these methods would be okay to show me intercepts. What you can't do is just tell me the intercepts are 5 and 1 with no work. That ain't gonna fly. Then you miss it. So you can either do it this way, or you can set it up to be done in your Casio, and then at the very end, you can put it in your Casio, or you can factor it. I mean, obviously this thing would be very easy to factor. So, you know, by having you put it in the Casio, I'm saving you one line of work, so it's not that big a deal. But there is definitely work involved in finding those intercepts. I mentioned this test might be a little harder than last one. Just checking. Any other ones? No? Oh, you better just wait till the weekend again, okay. So, let's go into more crazy time. Polynomial rational inequalities this time. So previously, we've had several kinds of inequalities. We have had this kind of inequality, where, you know, it would say like, you know, solve for x, and you would solve this. You would possibly graph it on the number line if you needed to. You would realize you need a square bracket here, and you do that. And your final answer would be 3, 2 infinity. Okay? So the difference between that and what we're gonna do now is now we're gonna do quadratic inequalities. And the difference in solving a quadratic equality is the difference between solving a linear equation and a quadratic equation. They're totally different styles of solving equations, okay? And solving quadratic inequalities, also totally different, okay? So first thing, what you wanna make sure is that you rearrange the inequality so you have one side set equal to 0. So these things can look like anything. But just like with a quadratic equation, I rearrange so I get everybody equal 0. For the inequality, I rearrange so I have 0 on the other side, but it could be anything, less than, greater than, less than or equal to, greater than or equal to. It doesn't make any difference which way the inequality sign points, okay? So I would start off this one by distributing the x, and then I'd move the 15 to the other side. Okay, so I'm going to be factoring this because that's how I solved most of these quadratic problems. But I have to interpret it a little differently. So first of all, if I tell you, let's say, well, let me go ahead and factor this. So let's say I have x minus 5, x plus 3. And I say less than or equal to 0. So then I'm wondering, why can't I just say x minus 5 less than or equal to 0, x plus 3 less than or equal to 0? In other words, the same thing I would do with a quadratic equation. Two things multiply to give you 0. That means either the first one's 0 or the second one is 0. The problem is, it doesn't work that way with inequalities. Because I'm not saying equals 0 here. I'm saying is negative. When I say those two things multiplying together, the only thing I know is that I'm getting a negative answer when I do that. Or 0, because I do have a little equal sign. So I can't split them like this. I can't say I multiplied two numbers together, I got a negative answer. That means the first one and the second one are negative. No, it's more complicated than that. In order to get a negative answer, one of them is negative and one of them is positive. That's how it works, okay? And if you want to give a positive answer, they both have to be positive or they both have to be negative. In other words, there's a lot of different cases if all you're talking about is the signs. So we don't do this. What we're going to do is we're going to do like a big global analysis that finds out where this particular polynomial is positive or negative for its entire domain. And then at the end, all I look at is the one I need. If I have a less than sign, I pick the negative answer. If I have a greater than sign, I pick the positive answer. But my analysis goes for everything. It doesn't matter if the sign's to the left, to the right, has a little equal sign, doesn't have it, completely irrelevant. So I'm going to find what are called critical values, which are where this thing equals 0. In other words, your ordinary polynomial. So I've got x squared minus 2x minus 15 equals 0. That's x minus 5, x plus 3 equals 0. That's x equals 5, x equals negative 3. So these are what are called boundary points, these critical values. This is where a change is going to occur, possibly from positive to negative or negative to positive. So I draw a number line, and I put in these points. And then I have 3 regions in this case. And I want to find out what is the sign on my polynomial in each region. So the easiest way to do that is to pick a test point in each region and plug it into my polynomial. So in each region, I'm just going to pick a number. So negative 3 forever. So I could pick, say, negative 4. In between negative 3 and 5, I can pick any number I want. Pick negative 1, positive 1, 2. The easiest thing to pick, if it's available, is 0, so that's the one I'm going to pick. And then pick any number bigger than 5. So usually I just take the first nice number that's bigger, so that'd be 6. Okay, but you plug in 50, you could plug in, 112 over 17, whatever number you want, okay? And now I'm going to plug these numbers back into my original polynomial and see if it gives me a positive answer or a negative answer. Now, if I'm plugging them in, I usually plug them in to here, the one where I factored it. Because it makes it easier to calculate. But you can plug it into the original one if you want to, where you haven't factored it. So I'm going to say I have negative 4 minus 5, negative 4 plus 3, that's negative 20, -1, that's +20. Okay? But in reality, I don't even have to do that much work. The only thing I'm interested in is that. I don't care if it's 20 or 3,000 or whatever, the answer is positive. That's what I wanna know. So if I,
Is it negative 1 minus negative 5 or?
no, I'm plugging it right in here, -4 minus 5. Oh yeah, -9. Like I said, that's why I'm not paying attention to the number. Is that what you were asking me? There you go. Okay, so that means for every number I would plug in that region, I would still get a positive answer. All different answers, but it would be positive. If I plug 0 in, I'm gonna get a negative answer. So everything I plug in from here to here gives me a negative answer. And then when I plug in 6, I'm gonna have 1 times 9, it's gonna give me a positive 9. So now I get a positive answer. Okay. And again, the only thing I'm interested in is the signs. In other words, if I didn't even use, yes,
Is the region 4, isn't it multiple?
-9 times -1.
yes. So I've got all these signs floating around here, and that's really all I need to pay attention to, which explains why I'm not paying attention to the numbers, okay? What I really need to pay attention to here is, this is a negative times a negative, which gives me a positive. This one is a negative times a positive, which gives me a negative. And this one is a positive times a positive, which gives me a positive. So you don't even need the actual number. I don't even have to figure out what that is. I know it's negative, and a negative times a negative gives me a positive. And that's what I'm interested in. This ultimate answer here. So that tells me where this polynomial is positive or negative over its entire domain. Okay? So, then what I do is, say, what is my sum? Okay? So for that, I go back and I look at the original one. Here is my sign right up here. Okay, x squared minus 2x minus 15 is less than or equal to 0. In other words, my sign is less than or equal to 0, which means negative. That's what it means. That's the literal definition of what it is to be negative. You're less than 0. So my answer is where this thing is negative, which is from -3 to 5. And that's my final answer. If the original question had a greater than sign, these two regions on the outside edges would have been my final answer. So it's the same analysis for every single question. At the end, you look at your particular sign and you say, okay, do I want to write down the positive intervals or the negative intervals? That's my final answer. But for when you're doing the analysis, you do it globally. You do it everything from left to right. So I'm not actually finding out where this thing is in particular negative. I'm finding what sign it has everywhere. And then I pick out the one I want. You can also see this with the graph, because I know by now you know that's a parabola. And you could graph it, it's a parabola pointing up. The x-intercepts are -3 and 5, because that's where it equals 0. So that's where it's crossing over the axis. And if you were to draw a picture of it, that picture is also telling you, yes? How did I figure out this?
Yeah, like I know it's from up there, next equals, but,
It's from -3 to 5, that interval. I mean, I'm writing it in interval notation. Remember, like we did on test 1 with absolute value. Same thing, they're intervals.
why do you write, less than or equal to 0?
Because that's my original question. My original question was, what are you? Are you positive, are you negative? That's the original question. When I do the analysis, I ignore the sign, which way it's pointing. But when I go to give the final answer, I gotta look and see which sign I actually had. So if I were to draw the parabola, I would see positive up till -5, meaning it's up above the x-axis. Then it's negative from -3 to 5, meaning the graph is below the x-axis. And then it's positive again. So you can actually do this from a graph. You could graph it and see where it hangs below the axis or above the axis. Now, it's not practical for us because it takes longer to graph than it does to do the analysis. But if you were in another class, like say my pre-calculus class, where they have graphing calculators, you could do it graphically because you could do the graph on your calculator. And your calculator, you would see the picture and that's the analysis, okay, the actual graph. So I know you're all looking at me like, what the hell?
Out of curiosity, in that loop, it comes around in the graph. It comes around the 15. Does that tie into?
Well, that would be the vertex.
Yeah. So that does tie into the one in the middle, the one that has negative, up there.
Yeah, well, I have -10. Yeah, -10, 15. Unless I did the graph wrong. Yeah, that's the graph. Oh, that's a different one. Never mind. No, it's still not the right one. Oh my god. So, x squared minus 100 minus 2x. In other words, if I change the sign, the analysis wouldn't change. I hope that's a graph of that. I'm hoping it is. So, is there work to show? Yeah, obviously. A lot of work to show. I forget if there's 3 of these, I think? Or 2, I think there's 3. Okay, so here we go. First, make it look like something you went back. So move the 15 over to the other side. So this means I'm looking for where it's positive or where it equals 0. In other words, where my final answer is going to be where this polynomial is positive or equals 0. The equals 0 part just means I'm going to have square brackets on the end. That's all that means. Other than that, it's okay. So first I find the critical values. And that means I pretend this is equal to 0. And I factor it. Or use your Casio to factor it. So I will have x equals 5/2. X equals -3. And I use that to draw my number line. So I've got -3, 0, and 5/2. So I have 1, 2, 3 readings. So I am going 5 halves, so that's 2.5. So here, I'll put in 3. So when I do that, I'm going to have -8 minus 5 and -4 plus 3. So that'll be a negative times a negative, which is a positive. I don't care what the numbers are, I just care about the sign. Here I will have 0 minus 5, 0 plus 3. That'll be a negative times a positive, that'll be a negative. And over here I'll have 6 minus 5 and 6 plus 3. So that'll be a positive times a positive, which will be a positive. So I've got positive here, negative here, and positive here. So my original problem is positive. So that means I want these intervals, so that's here. So my final answer is going to be negative infinity and negative 3 union 5 halves to infinity. Split either side. Yes,
It's always gonna be positive, negative, positive.
no. It could even be positive, positive, negative, or negative, positive, positive. That's why you do the analysis. So, wouldn't it be nice if your Casio could do this?
Yep.
You can. For a small window, it can't do them all. It can do quadratic inequalities. Now, you can have worse than quadratic inequalities. That's a cubic if you were to multiply it out. Notice it's nicely factored for you, but that would start with an x cubed, so your Casio can't do that. And your Casio can't do that. But the first two, it could. And once again, that doesn't mean you get to show me no work. That means you should know what the freaking answer is and you have to justify your work, okay? So, on my Casio, under mode, it's not an equation, so it's not gonna be under that menu. But notice that here I have a little arrow. So go down and look at what I have. That's an inequality. And look at my choices. Quadratic. And there they all are. So let's do number 2 here. So greater than or equal to 0. So that's choice 3. So it looks like the same kind of menu we had before. Notice you have to have it in terms of 0, just like when you're typing this stuff into your Casio for a quadratic equation. It has to be 0 on the right-hand side, it has to be 0 here. So you could still screw this up by not simplifying correctly to get the 0. But I have 2 in front of the x squared, I have 1 in front of the x, and I have negative 15 for my constant. And there's my answer. Not in interval notation. This says x is less than or equal to negative 3, and x is greater than or equal to 5 halves. Okay? It's saying, remember, you always read from the point of view of x. So it's saying this, less than negative 3, greater than 5 halves. It's just not writing it in terms of intervals. Okay? It says x less than or equal to negative 3, and it says 5 halves, like this. Oh, now you're gonna listen?
No, I was just trying to fill in and.
Okay. Go back to mode. You need to arrow down. You want an inequality. See, there's no inequalities in these lists? So do the little arrow, now it says inequality. And I want a quadratic inequality. And there are my 4 versions. Now, truthfully, this is kind of long to get there, and then you have to interpret it, so it's not quite as useful, I don't think, as the one that solves quadratic equations, because that's really straightforward. And you could still screw this up, because like, say, right here, you wrote plus 15 instead of minus 15, you know what I'm saying? It's only as good as the simplifying you do to get to 0. So if you mess that up, you're probably gonna mess up a lot more. I think this analysis is pretty easy. So, this one is already factored. So I don't have to do the factoring part. I can just start by saying, yeah, what are the critical values? No, just positive 2. Because it's what I put in there to get a 0. So it's gotta be positive 2 and negative 3. The positive 2 occurs twice. That's the difference. But there's only one number that's gonna make that 0. If it were x squared minus 4, that's a positive 2 and a negative. So I've got 2 numbers here. I've got negative 3 and 2. My 1, 2, my 3. I'm going to pick negative 4 back here. I'm going to pick 0 here. I'm going to pick 3 over here. So in this one, I will have negative 4 minus 2 squared times negative 4 plus 3. Well, here's the thing. That is positive no matter what, because you're gonna square it. So it doesn't matter what number you put in there, it's always gonna be positive after you square it. So this is going to be negative, where I will have 0 minus 2 squared, 0 plus 3. So that will be positive and positive. So that will be positive. And here I will have 3 minus 2 squared and 3 plus 3. So that will also be positive and positive. So this one doesn't alternate. My answer is where this thing is greater than 0. Okay? So it is where greater than 0, but it does not equal 0. Okay? In other words, there's no equal sign underneath there. So this is where it's greater than 0. So even though it looks like that should be everything here, I have to skip 2, because at 2, it equals 0. It's not positive or negative, it equals 0. So this one, my answer is going to look like this. Minus 3 to 2, 2 to infinity. If the original had been this, that means positive or equals 0. My answer would have been minus 3, minus 3 to infinity. Because I would have included 3, and it would also include the 2. So totally different answer. Notice that all I have to do is switch these signs around and you get completely different answers. Even though the work is gonna be the same for all of them. Anything that has an x minus 2 squared and an x plus 3, it's gonna have the same work, but the final answer you give me is gonna change. If this had been x minus 2 squared, x plus 3 less than 0, then it would have been the negative part. So my answer would have been minus infinity minus 3.
But neither of them would be our answer, I don't think that's not.
Right. I'm just saying, all you have to do to make these different problems, even though they look like they're almost identical, is switch the signs. In other words, this part of the problem, this main stuff over here where all the work is, all the work is the same, no matter what it says. Less than, greater than, less than or equal to, greater than or equal to, completely irrelevant. That whole structure where you figure out the critical values, you make your little, picture on the number line, you analyze whether it's positive or negative, that's the same work for every single problem. But the final answer can be totally different, depending on which way the inequality sign goes. So you have two pieces of this, the work, which is actually relatively simple, and the analysis, which is where you stare at what you have written down and figure out which piece of that picture is your actual answer. So, products. And you know, this could be as many as you want if they're already factored for you. We can't factor much but quadratics, but I can give you 3 or 4 things if I, products, if I have them factored. But we also have quotients, because it's polynomial and rational inequalities, and rational inequalities to tell you why it's in this particular section with rational expressions, particular chapter. So for the critical values, I have 2 places where I have the critical values. I have where the denominator is undefined, which in this case is where x minus 2 equals 0, so that's x equals 2, and where f of x equals 0. So the only way that thing equals 0 is where the top equals 0. So those are my 2 values. So I've got negative 3. There we go. Oh my god, do I have negative 3 for a freaking critical point in every problem?
Yeah, you did.
Oh my god, every single one, what the hell? Clearly my favorite integer. It's just weird. So again, I'm trying not to make them too big. I'm thinking, okay, I don't want it too big. No, 5's too big. Well, I don't like 4. I guess it's 6. Every time. Okay, so I still have 1, 2, 3. I still pick whatever point I'm gonna plug in. By now, I guess we know.
Negative 4.
Yeah. I think it's the only freaking point I know. We got negative 4. We got 0. We got 3. Now I'm gonna do my analysis. Now, the analysis is also the same, because the rules for whether something is positive or negative, it's 2 negatives make a positive. It doesn't matter if they're multiplied or they're quotients. 2 negatives make a positive. So it's the same kind of analysis. This time I'm gonna put in negative 4 up top and negative 4 down here. So that will be a negative over a negative, which will be a positive. Same thing. If they were beside each other or on top of each other, it doesn't make any difference. Same analysis. Here I will have 0 plus 9, over 0 minus 2, so that will be a positive over a negative, which will be a negative. And then here at 3, have 9 plus 9, over 3 minus 2, which would be a positive over a positive, which would be a positive. So here, I will have have positive. Here I'll have negative. And here I will have positive. And now I go back, same as before, and look at what my original one was. My original and it has to be negative or it has to equal 0. So that means I am looking for here to here. So it's from here to here. Now, here's where I have to be careful also. My answer is going to be -3 to 2. Not with the square bracket. Because 2 is in the denominator. So whether it was supposed to be equal 0 or not, it can't equal 0 in the denominator. So here is where this test is going to screw you up. Look at how teeny the changes are in those answers as far as the symbols that go on the end. Okay, that's what's going to make you crazy, because it's super easy to make the answers choices for these. I can have -3 to 2. I can have -infinity to -3. 2 to infinity. I can have -3 to 2. Okay, I have 2 letter B's. Good. And I can have -infinity, -3. Okay? So those answers are buried in there is the correct answer to the negative version and the correct answer to the positive version. Okay? Each of them. This is the correct answer to the positive version, where it's these two. This is the correct answer to the negative version, but you gotta decide between those two. And, to make it even better, if the original problem had not been a quotient, okay, so if the original problem had been, what is it, 3x plus 9, x minus 2, in other words, they weren't a quotient, they were a product, then my answer would be -3 to 2, closed. Because now I'm allowed to have an equal 0, because it's no longer in the denominator. But the analysis is the same.
So you basically only have to worry about it between the denominator for
Right. It's like domain problems. There was a question on some of the tests where the square root or something was in the denominator. If it's in the denominator, you have to throw out the endpoints. Okay, where it equals 0. So the analysis is not hard, the factoring is not hard, but giving the answer, you really have to pay attention to the little teeny details. That's what's gonna kill you. And on a test where you're nervous and this and that, it's easy to let those things slip by. You really gotta check these carefully. Because they will have all the different versions of this answer possible. They don't think you're gonna do something weird like you get a 5 and a 7. They figure you're gonna get the numbers. The question is, are you gonna do the analysis right to give the correct version? And then we have help. And it doesn't look like it's that much different, but it's the same problem that we had before, because with this one, it has to be a 0 over there on the other side. I can't say, I have a quotient and it gives me 3, and I can somehow do it in terms of 3. It always has to be a 0. So that means I have to put the 3 on the other side. And now I have to put those two together, because I need a single fraction. I can't do the analysis unless I only have one fraction. So that means I have to get a common denominator, which is x plus 2. I have to multiply on the top and bottom by the common denominator. So that will give me 4x plus 5 minus 3 times x plus 2 over x plus 2. So that will be 4x plus 5 minus 3x minus 6 over x plus 2. Okay, 4x minus 3x is x, 5 minus 6 is minus 1. That's where you start your analysis. Okay, so it takes a lot more work to get this to be a single fraction. I know you remember this, right? From way back in your past. Remember that test you made in February?
Wait, why, multiply the x plus two to the denominator? No, I don't know.
You mean multiply both sides by the
Yeah.
denominator? No, because I don't want the denominator to disappear, it's gonna give me a critical point. So I'm not clearing the denominator because that's one of my critical points. In other words, my critical points are gonna be x equals 1 and x equals negative 2. If I multiply both sides to get rid of the denominator, that denominator part would disappear. So yeah, I wanna know where x minus 1 over x plus 2 equals 0, or it's undefined. So it equals 0 when x equals 1, and it's undefined when x equals negative 2, the denominator. So that gives me, oh my god, look, I don't have negative 3. Negative 2. There's my 3 regions. And I have, let's see, no, I've been picking negative 4 for so long, I feel like I should be picking it. I've got negative 3, I've got 0, I'll use 2 back here. So that's gonna give me, negative 3 minus 1. Negative 3 plus 2, so that's a negative over a negative, so that's positive. I've got 0 minus 1 over 0 plus 2, so that's a negative over a positive, so that's a negative. And I have 2 minus 1 over 2 plus 2, so that's a positive over a positive, that's a positive. So I wanna know where my thing is greater than or equal to 0. So that is here and here, where I have positive. But do not include that number, because that came from the denominator. So when I go to write my intervals, final answer is going to be minus infinity up to minus 2 and then 1 to infinity.
Yeah.
Sure. Yes, homework. I mentioned you need to do that. Every day I check in, I got like 2 more people missing from my roll. What do you think I'm gonna lose after that? This might be a 3. Yes? Should I ignore you for too long? I'm sorry, yes.
Is there ever a time when you can't do 0 for one of the numbers in the second?
Well, 0 could be the border, then you couldn't pick it. In other words, it could go, you know, if zero's on the border, you'd have to pick to the left or the right, so.
Let one of the X values on zero and put it to
Right, in other words, if you had an X times something. So let's say you had something that factored. Oops. Sorry. That was weird. Let's say you had something. Kind of like this. That single X is gonna mean X is 0, or it's -1, or it's 5. So you would have -1, 0, and 5. And you would have more regions also. You would have 1, 2, 3. And you couldn't pick 0 because it's on the edge. So you pick like -1 and 1 in those two different regions. Or actually -1 is there too, so that would be more like minus a half. But usually you can pick, you know.
Professor, why does number 1 have a bracket in the answer?
Because my original inequality had the line underneath. So if that 2 wasn't in the denominator, it would also have the square bracket. In other words, when you have that line underneath, this is what you usually see is the square bracket. This one is the odd one out because it's coming from the denominator. If these were next to each other, they both have square brackets. So, these three inequalities, which would give you totally different graphs and look totally different, have absolutely identical analysis, okay? They all have the same critical values. You would find out where they're positive and negative. You would do everything exactly the same, but the final answer for each one of those is going to be different, okay? So the key thing is the analysis, okay? They all have critical values of -5, -2, and 3. Me too. And then I pick around on either side of those, and depending on which one of the 3 I have, some of them would get, you know, a square bracket, some of them would get curves, but the analysis where I figure out where these things are positive and negative, absolutely identical. I don't, once this is in, how I'm plugging them in, doesn't make any difference. What is that one for you guys? I think at this point, watching me do one of these things is just torturing you. Oh my God, my brain's already popped. They're not bad. When you start doing them, you realize they're not difficult. Okay? But they are tedious. Yeah. That's it. That's it. How much more can I torture you? Look, I'm fine. I think that's enough.